Hi, everybody. My name is Antonio. Here with me, we have Leo. And today we'll have our talk, More Data Please, and on Green Cloud experiments. Actually, I've looked this up. It's been, more or less 20 years. The term cloud has been out. So, in these 20 years, we recently had the 10 years anniversary of Kubernetes. So it's a very established industry. And we all know why the dream of the cloud has become true. So we have scalability, so a lot of resources on demand, agility, so the faster dev for the cycles. And there are a lot of abstraction, right? A lot of complexity that has been made simple. On the other hand, we have some hidden costs. So we have energy demand that we rarely measure. And also, we have infrastructure detachment. So actually, the first time I saw a server was this year, and it was you had this noisy, big machine that takes a lot of heat. And it's I never seen one, right? I never had to see one. I don't know how many people can relate. But it was quite impressive. And we are getting towards a world in which you're more oriented to application development and a little bit loss of technical knowledge to the deeper stack. So on the other side, we also have software that gets bigger in a way, right? Hardware has never been easier to provision. So just a click away, we can have more compute, more nodes. And our software just gets bigger and bigger. I remember we had some discussion because we ended up having Docker files or Docker images that have 2 gigabytes in size. And maybe this was not possible 20, 30 years ago. And that's maybe because we have memory bloat, so we don't care what allocation we do of the memory. We have execution bloat, or simply we have environmental blind spot. So how did we get there, right? It's hard to answer. Probably the reasons are different, but probably also abundant compute as an answer. So why optimize when it just takes 1 second to put one more node on a bigger one? So it's just cheaper to go this way. Or also the fast market has pushed us to develop more and more features, right? That's what we call feature creep. And also there are so many layers that if we have to deep dive, maybe we just not able to, because we don't understand a lot of layers that are deep behind. So that's why we wanted to set this talk. And I'm gonna give the word to Leo, who's gonna talk about environment setup.
Right. So I think in the community and also in general, in the sustainability and environment area, most of the discussions are pretty high level. So it's abstracted away, and it's not so often about actually what it's about, right? So you have resources and energy, so it's a very low level kind of thing. But because we are in the cloud, we are talking about workloads, about services and everything. Everything is abstracted away. And that was, as Antonio said, sort of the idea, just to sort of turn the table, not coming from the top and going down, but actually starting from the source. So bottom up, so to say. So if you look at the entire environment, this looks very different, obviously, from company to company. But in general, it's very complex. And this is already a very simple view, but you have different types of how you structure your network, how you communicate, how your workloads are, if they're small, if they're large, where your geolocations are located, are you a global business or not a global business? And that's just from a topology standpoint already very complex. So when we started thinking about, okay, when we want to start, how do we start? Okay, let's just focus on perhaps one region, on compute, starting a little bit small and then growing perhaps later. So all the measurements that we do later in this talk basically are focused in a very capsulated environment, which is in some ways not very much near to the reality, because rarely you have a very capsulated environment, but still it's sort of where we started. So I said we want to go from the bottom up, right? So what does it mean? It means that we buy hardware, that we just as Antonio said, look at servers, not for the first time, but sort of. Getting into bare metal, thinking about, okay, how does storage look like? How different types of storages do you have? And not just like an abstracted kind of way from cloud providers where you have different storage tiers and whatever it is, but actually the bare metal part. And this sort of led to building this kind of device, which is just a bunch of compute units, a switch, and cooling, so fans which are connected, and so on. So you have something to play with, but also you always sort of stay in touch with the hardware itself. So you're not getting sort of disconnected. And if you build later Kubernetes clusters, services, and so on, you always can sort of have all the way through to the hardware to have like some kind of understanding. And then hopefully sort of the information can be transferred also to your more production environments. At least that was the idea, or it's the idea. So this is sort of how it's structured. Pretty simple. So we have 4 different compute nodes. They are all the same. So there can also be a lot more variety, right? So if you want to do different ARM chips and so on, this could be like a very interesting comparison in the future. But these are all Intel mini PCs, as you saw like in the previous one, stitched together, connected over a switch. One of the nodes is responsible for sort of being the gatekeeper. It does DNS and netting and so on and so forth. This is for sure not like the best way to structure this, but it also gives like a good idea if, for example, node 2, node 3, node 4, with the Kubernetes cluster want to access the internet in some ways, they have to go over node 1, which is sort of interesting in terms of measurements, because then you can isolate the environment a lot more. Right, so if we put some stuff on this to actually do something, we chose to go with K3S, which is kind of simple to set up in a NixOS environment. It's like something on the next slide. So with NixOS, you can just have like a very easy configuration, so you can spin up a bare metal cluster without a lot of hassle. This is, again, also probably like in a larger environment, a little bit different, but for our purposes, I think this served quite well. So all the components which you see at the top are basically just like the default configuration. We did not change a lot, besides maybe IP addresses and so on, but all the other stuff, like in terms of like setup, it's all default. All the optimization that can be done is for us like an experiment to see, for example, if you want to change like CNIs, for example, like how does this compare? And then for energy measurements, we chose Grafana, which is a project. There's also a slide later about this, just to measure the energy consumption. So that's the setup. Right, and I said this is all like configured with NixOS. This was like primarily also in a way like self-driven, a learning experience, getting into this entire rabbit hole of other technology, which is also very interesting, probably also like in other environments. So Nix is a lot of things. It's a package manager, so you can also use it on your macOS notebook or whatever, just to configure basically as like a homebrew variety, basically your entire packages. But it's also, you can also use Nix to declaratively sort of describe container images, which then can also be sort of compiled to virtual machine images, QEMU images, or for entire NixOS Linux distribution, also for bare metal. And what is very cool is that you can, as I said, have like a declarative way. So if you want to open certain ports, you define this in your NixOS configuration, then you rebuild, apply the system, and that's quite cool. And then because there's multiple machines, I used a project called Colmina, which sort of wraps the entire environment into a system closure, and then you deploy this entire sort of system closure to the thing and make updates based on this. So very interesting piece of technology, I think. Also in terms of like reproducibility, and also if you want to sort of track your changes, because if you use Nix Flakes, you always can guarantee that inputs always are resulting in the same output. But this is not about Nix. But still, this was used. And then I mentioned Scaphandra. So there's a couple of different ways to measure energy, which I'll describe on the next slide. But we chose Grafana to basically get all the different metrics, energy metrics essentially, about our workloads, and then we do like some analysis later. There are different projects that that do this kind of stuff. We chose Grafana because we know it and it works, and it's in Rust. Right. So what are the options to measure energy? So there's a couple of different ones. Like the most straightforward one in one way is like if you just go to sort of the wire, right? So if you put like some kind of device, if you measure the energy by the wire with a smart meter or by hand. So that's the one below, basically. The one above is over the BMC. So if you have a server, usually like in data centers or in larger like systems and servers, you have a bare metal controller which you can use to also access these kinds of metrics. So there's a small chip which basically does like firmware upgrades and whatever and so on. There's an entire like also API which you can use, and over this API you can get access to heat, to power, and a lot of other stuff. And then at the top, it's basically the software way. So it's like a correlation basically. So you don't go to the wire, but you use like events in the CPU basically to get a very good, very close, very accurate assumption of the energy that is being used. But RAPL and other implementations, so RAPL is the one from Intel. There are also other implementations if you use ARM or whatever. They are all software based. So it means there can be, as I said, like you do not necessarily have like the entire picture, because like if you stitch like different hardware components, they need to be like compatible with the API, and if they are not, you don't capture, for example, memory usage or something like this, right? So you can lose some of the values. So in our situation, we don't have BMC, unfortunately. Which would be very nice, but we do not. So we chose to go with the first one and the last one, essentially. And what is like the scope? So this is already in some ways, I think, clear to everyone, but I think it kind of makes sense to make this more explicit. So if you talk about like resource consumption and energy consumption, you can also have this like very broad, right? Because if you engage with software, you also use like some kind of monitor that's also required. It also draws energy. So there's like a lot of like first level, second level, third level sort of energy usages. Also in usually or perhaps like in systems you have some upstream APIs that you consume, or some SaaS application that you just sort of bought, someone's cloud environment that you borrow in some ways or that you use for your system. So all these different kinds of dependencies also consume energy, and it's difficult to get the entire picture. So the overall scope is very large, it's complex. So it's sort of like what we reduce because we have like the capsulated environment. So what we can measure is actually just like a couple of the subcomponents, CPU and so on, basically what is supported by RAPL, and also what we can gather basically in the capsulated environment. So that's sort of our scope.
All right. So yeah, what we talked about was like why can't we try a day's journey? So we are all familiar with some kind of platform engineering. So here at day zero is the day you get some requirements, and maybe you're already lucky enough to get some Kubernetes running in infrastructure of your choice. And then day one is like application development. So we have our microservice developed. In this case, we took the Google Cloud microservice demo, which allows us to deploy on Kubernetes a microservice that would somehow simulate a real one. And then we wanted to also stress the hardware a bit. We use stress NG to see how the power measures would change when we have like high memory consumption or high CPU consumption. And then day three, we thought about, okay, what if we add some security constraints, right? Like we have some security applications, so not only we have our Kubernetes cluster really used and stressed, but also we run some continuous monitoring on it, like how is the power numbers gonna look like. And yeah, like we have very simple workflow because this is manual, right? It's also our first experiment, and we had fun with it, but it also took a lot of time to set up. So we have our manual run. We manually deploy our workloads. We manually deploy Falco, the microservice demo, and the stress NG pod. And then we launch a manual report of Scaphander. This is like continuous measurements for 1 minute, and we get PID level energy measures and power measures. And yeah, we have also a log file that we later use to show some of the graphs. But yeah, like question to the crowd: how much power do you think a single node in this configuration would consume?
In watts?
In watts. Someone?
Maximum.
Yeah, maximum power. Someone would like to give an answer? Yeah? 100 watts. 100 watts. Do we have more?
Or less.
We have less. 10. Okay. The man on the left say 10. Like who wants to say something different? 20. Okay, 20. Do we have some more? 5. Okay, we have 5. Yeah, we'll see this later. Okay, how much power is the home setup?
It's still the same. Oh, okay. Never mind.
So let's say it's 100. The entire setup, so like the 4 nodes, the switch, all the networking component. You have similar numbers? Let's see. So this is day 0, and this is the total cluster power consumption. So it's all the data of the 4 nodes, what we got from Scaphander, and cold means just Kubernetes running, and yeah, like it's very close to, like it's closer to 5 than any other numbers. So we get a prize for you later. And but yeah, like this is like even more close to 1, right? Like because I don't know, it's like less than 5, and it's the sum over the 4. So yeah, like it was funny because on the top you can see above 40, right? Like that's what we measured at the plug. So we expected something like 40ish, and from Scaphander we would just able to see less than 5. So it was already a bit concerning us. So we said, okay, let's try to deploy the microservice, and let's see how it changes. And it changed a little bit, but it didn't change much. Of course, the microservice demo in its basic form doesn't have a lot of interactions. So that's why we decided to stress it. So like, I think it's simulating 10 users in a minute or something, and it's like basic.
Yeah, so the microservice is like basically a demo application, I think by Google. Yeah. And they wrote, I think it's like 10 services or so. It's simulating like a web service, a web shop. And there is one of the services is basically just acting as a user, filling in the shopping carts, emptying the shopping cart, and so on. So different programming languages, different containers, and so on. So they try to, that's sort of the microservice that we deployed. It's not very heavy.
And then we decided, okay, let's try to stress the machines. And again, the expected power at the plug was slightly higher, between 50 and 80, so to say. But still the software measurements were not so like we're not capturing all of that, what was happening, right? And then, yeah, just for fun, we added Falco on top, so it's slightly more. So this is good, because in a way we're adding complexity to our cluster, we're adding complexity to the workload, and the power also adds up, right? So we can see this at least in our home environment, but we can also see that every time there is like some kind of offset that is missing, right? Maybe it's the power idle, maybe it's all the things that we cannot measure with software, but yeah, we were curious to see the numbers. And then, yeah, like here we have like this view a bit all together. So we have in gray the cold, so only Kubernetes running, then the microservice on top, just a slightly higher power consumption. We have those drops, probably that are related to how the stress NG works, but yeah, we didn't go very deeply into understand the stress NG, we just took them as outliers, and then like Falco on top is giving some more power usage.
Spikes, yeah.
Yeah. And then what we did is like, okay, what if we shift all the measurements by this cold baseline that we have? So let's say we have some sort of power idle that we cannot manage to measure, and we just shift all the measure by adding all these hardware-related power metrics that Scaphandra is maybe not able to capture, right? Are we gonna eat more or less what we saw at the plug? And we could see that, for example, for the microservice demo and the cold, like the ranges were hit slightly better, and also for stress and Falco. And interesting, maybe even the software is like capturing something more. So this was also an interesting finding.
So basically, if you account for the offset, the numbers that you get from Scaphandra are kind of accurate. So as long as you know the offset that is not captured, then you can just add this always on top, and then you have basically your number, which is representing the actual entire usage.
Yeah, but as we said, like this was our first experiments. It was kind of fun to go back to garage days and see what we would get out. Yeah, like we plan many more, and there is for sure a lot more that could be done. But this is for the Leos.
I mean, at the end, a lot of the projects in the CNCF also sort of relate to each other, right? So if you have, depending on your microservice, if you use Falco, this could have more impact or less impact, depending like on the services that you use. So understanding like these synergistic effects sort of is kind of or very interesting, just to understand how this works, and also to find out like how to sort of communicate those kind of effects back to the maintainers of all these different kinds of projects. Because if they are in itself scalable and so on, but there's like synergistic effects with each other which do not scale so well, or have like an energy footprint which does not shape so well, there would be, I think, interesting observations. But yeah, I mean, as we sort of like highlighted throughout the talk, there's a lot of different things we could change, which would have very interesting results, perhaps. So changing the host, for example, switching operating systems, or using a different kind of operating system, or using a unikernel, like a stripped down Linux kernel. Something like this could be kind of interesting for sure. Also using different kinds of chips, different kinds of hardware, how they all relate to each other, especially like using ARM, because ARM is always, from the architecture, more energy efficient. This is for sure like related also in those numbers if we would have an ARM PC in the mix. But yeah, just putting all these different, I think there's a lot of different like things that could be measured as well.
Yeah, I think we wanted to start a conversation about, yeah, like what is a right number, right? Like either power related or energy related. What is like, should I get worried if I get, I don't know, 100 watts or not? So we're really curious to have a I don't know, a number out of something that we could control, like on the stack, and that's the numbers we got.
Yeah. And I think the approach, like starting with the hardware and then going up, especially in terms of sustainability, makes a lot of sense, because I think that's essentially like the main issue, right? Because if you're like always very abstracted, you sort of lose touch and you don't really understand like all these like workloads that you ship actually consume so many different resources, and yeah, I think it's a good practice in a way. Right. Want to say any more?
No.
Cool. Right. I think we have a couple of minutes, so if you have any questions,
yeah, there is a mic there, I think, that works. If someone wants, or yeah, just feel free to ask one.
Otherwise, we will be also afterwards standing here for a bit if you want to chat. All right. I think then we can. Sure. There's a question. I'm not sure if I got the question right. Was it about basically there's like virtualization layers in between, so you cannot get the access to the bare metal metrics? Was it kind of your question? Yeah. So there's that's an issue. So if you don't, so you saw like one of the slides before, you don't have BMC access. You will never have BMC access like in the cloud environment, because this is like for the providers basically to orchestrate. It's also security sensitive and so on. And usually they also don't have a smart meter which you can hook in. So the only option that you have is something like RAPL. But in virtualized environments, this is capsulated, so you cannot access those metrics. So in those situations, it's not possible to get those kinds of numbers. But what you can do, there's another project called Kepler, which basically does like some fancy machine learning, basically to get very close to those numbers. But the issue is, as far as you sort of abstract away from the hardware, and this already happens with something like RAPL, even if the margin is like very tiny, as further as you abstract away, as bigger as the correlation basically grows, and then it's difficult to make actually the exact numbers, right? So you have like a bigger margin of error, but it can be done. You can get pretty close. That's something I think which we also put on this slide. Doing measurements like in a virtualized environment where you have like another hypervisor or something in between. Yeah. All right, cool. Then thanks everybody for joining.